Okay, first thing I want to note is that I'm recording these in a slightly different order than the assignment this term. So, what you'd want to do is skip ahead to the chain rule videos. With those chain rules, I only use the power rule, which we've had a lot of practice with so far. And then in here, I'm mixing in the chain rule along with these derivatives of exponential functions. So my tip is go watch those two chain rule videos first to get some practice with those power functions, and then we'll see how it comes up in this section. All right, so with this are two derivative rules. So exponential functions is where we have some base and our variable is up in the exponent. So there's kind of two ways this shows up with E. So this is our continuously compounding exponential function that we talked about in pre-calculus a bit. So E is just a number, but it's just a special number that comes up with this idea of continuously compounding. But basically it's a number raised to an exponent of x, but it's a very special one because whenever we take the derivative of e to the x, we're just left with our original function, which is so nice. So if we're taking the derivative of e raised to the power of x, it just stays e to the power of x. If we take the derivative of absolutely any other number as the base with our variable in the exponent, what we'll do is we'll keep that exponential form, but also we need to multiply by the natural log of that base value. So really, these rules are the same. It's just if you plugged in e there, that turns all into a big 1, because the natural log of e is equal to 1. So really, always this rule works. Even here, it's just nice to just remember derivative of e to the x is e to the x. So let's try out these rules with some different derivatives and mixing in our other rules as well. So taking the derivative here. So we're subtracting two things. We have this e times x to the 5th power, and we have this negative, or we could think of this subtraction separating them. So we have this 3e to the 6x power. So what we're going to do is take the derivative of each. We're going to take the derivative of e times x to the 5th power, and then we're going to subtract that derivative of 3 times e to the 6x. Okay, so this first piece, let's just kind of read through what we have here. So we have e. And what you want to just keep in mind is that e is just a number. It's almost equal to 3. So like a 2.79, I think. So that's just a number. So really this is a constant multiple. We have a number multiplying with is x to the 5th, which our derivative rule says that stays, and then we just take the derivative of x to the 5th. So what we're going to have here is we're going to keep e multiplying. That exponent of 5 comes down, times x, and then a 5 minus 1 to get an exponent of 4. And that piece is done. We can rearrange it a little bit to make it look nicer in the next step, but for now, that is perfect. Minus 3e to the 6x. So again, we have this constant multiple, so that 3 is just going to keep multiplying. Here, this is going to use the chain rule. Because at the outside of it, we have just base and exponent. So we have something exponential on the outside of it, but we have this inside function of 6 times x. So taking the derivative here, we're going to have that 3 hanging out. We're going to multiply. So derivative of the outside function, so e raised to a power stays the same. So it stays e to whatever power, and we keep our inside function. But what we need to do is multiply on the derivative of the inside function, which would be the derivative of that 6x, which would just leave us with 6. Ooh, I wrote that very big. Sorry, I got zoomed in there. But Hopefully that just makes it more visible. So, simplifying this down. Our first term, we have 5 times e. It's just nice to have the number first, so 5e times x to the 4th minus 6 times 3 is 18, and then we have e to the 6x power. So, with these exponential forms, this is going to be kind of the theme for the chain rule, is that the base and exponent will be the outside function, so you'll just be taking the derivative of that, keeping that exponent pretty much the same, but then you always need to multiply on the derivative of that exponent. All right, let's go ahead to this next one. So here we are multiplying two things, so we have this x cubed and e to the negative 2x. So with this, we need to use the product rule. So taking the derivative, we're going to have our first function times the derivative of the second plus our second function times the derivative of the first. All right, let's simplify down. So x cubed is going to keep hanging out there, taking the derivative of e to the negative 2x. So this is similar to what we just did in that last example where we have this inside function of negative 2x. So derivative of e to any exponent, when we take the derivative of that outside function, it just stays e to that same function. We keep that inside function times the derivative of the inside function, so derivative of negative 2x, which is negative 2. So these two pieces together make the derivative of that piece. And then we're going to add on, we have e to the negative 2x times the derivative of x cubed, which is going to be 3x squared. And then we're just going to simplify down. Let's see, this is going to be, let's, there's a few things we can do here. And if you're probably noticing, that's the theme with these in terms of simplifying. I'm going to take care of these negative exponents. So what that's going to do is, in the numerator, we're still going to have the negative 2, we're still going to have that x cubed, but we're going to have e to the positive 2x in the denominator. And then we're going to add on, we have 3x squared is staying put in the numerator, but moving to the denominator is the e2x. And what's nice is that we have a common denominator there, so what we could do is go ahead and add those together for a negative 2x cubed plus 3x squared all over e to the 2x. And we could leave it like that. Could even go a step with factoring out x squared in that numerator. Usually, if we think about factoring the numerator, it's to try and cancel things with the denominator, which factoring out an x squared isn't going to do anything with that denominator there. All right, with this one, we are getting the quotient rule here because we have numerator and denominator. We can see, if you're wondering, like, but where's our exponential part? It's right there with the 4 raised to the t power. So this is going to use that second rule where we take the natural log times our base and exponent. So, quotient rule. Let's go ahead and make a note of what rule we're using. So with the quotient rule, we're going to start with low d high. So low, the denominator, 3 plus 16t cubed, times the derivative of the numerator, which is t to the 4th plus 4 to the t. And then we're going to subtract high d low, so t to the 4th plus 4 to the t, times the derivative, I wrote ddx, but it would actually be ddt. It's just a notation thing, of 3 plus 16 t cubed. All over low So we're taking 3 plus 16t cubed and squaring it. All right, let's take some derivatives. So we have 3 plus 16t cubed, that's going to stay there. Taking the derivative of t to the fourth plus 4 to the t. So we have addition, so we can find these derivatives separately. So derivative of t to the fourth is 4t cubed. And then we're adding derivative of 4 to the t. So if we go back to our rule at the top of the page here, so if we're taking the derivative of, dx dt of 4 to the power of t, what we're going to have is the natural log of the base. So we're going to have natural log of 4, and then times keeping that base of 4, and then exponent of t. And we don't have the chain rule here because there wasn't anything extra going on in the exponent. But if that was like 2t, then using the chain rule, you would multiply on derivative of 2t, which is 2. So that could happen. All right, so derivative of 4 to the t is a natural log of 4 times 4 to the power of t. And then we're going to have minus t to the fourth plus 4 to the t times, let's see, derivative of this 3 plus 16t cubed. Really, we're just focusing on that 16t cubed. So we're going to have 16 times 3 for a 48, and then t squared all over 3 plus 16t cubed squared. All right, simplifying down, that becomes our next piece. So we've done the calculus part, and then it's just a matter of simplifying. So what I'm gonna do is up here, we're gonna distribute the 3 through, and then we're going to distribute the 16t cubed through. So what that will look like is 3 times 4t cubed, 12t cubed, 3, let's see, plus 3 times natural log of 4 times 4 to the t. Okay, so that distributed 3 through, distributing 16t cubed, so we're going to have plus 16 times 4 is 64. T cubed times t cubed, you add those exponents together, so that's t to the 6th power. And then we're going to have plus 16t cubed times natural log of 4 times 4 to the t. So let's see, we're going to have 16 natural log of 4, and then the t cubed, and 4 to the t. Oof, that's messy. All right, and then minus. And over here, we're going to distribute that 48t squared. So I'm going to keep those parentheses going. 48t squared times t to the 4th, so that'll be a t to the 6th. And then plus 48, and then t squared times 4 to the t. And then we're distributing that negative in, so to drop those parentheses, we just need to subtract both of those. Okay. Okay. 16t cubed squared in the denominator. All right, our last step here, at least I think so far. Let's see if we can combine anything, which we can combine that 64t to the 6th and negative 48t to the 6th. Let's go ahead and take care of that. 64 minus 48 is a 16. So we'll have 16t to the 6th. Let's see, t cubed, nope. Yeah, no other like terms in there. So everything else is just gonna stay as is. So I'm gonna go plus t cubed plus 3 natural log of 4 times 4 to the t power plus, I'm gonna go ahead and do minus that 40. Oh, yeah, those are no, sorry, I thought I saw a like term, but it's not. Negative 48t squared times 4 to the t plus 16 natural log of 4 times t cubed times 4 to the t all over 3 plus 16t cubed squared. Oh, what a mess. But hey, there's our derivative. That would be the derivative. Especially with that base 4, it just gets messy with those natural log. It kind of makes things harder to combine with each other. Okay, 3 more here? 4 more with a word problem? Okay, this is just going to be a long video, but go for it. Again, what you could do is pause the video here and try these next ones for yourself too, because that's really the best way to learn with these complicated derivatives is try it, then compare and contrast your answer to see if we end up at the same spot. All right, this is going to be quotient rule because we have numerator and denominator. So low D high times high D low, minus high D low all over low low, so x to the 5th squared. All right, next piece here. So we're gonna have x to the 5th times the derivative of e to the 3x. So this is gonna use chain rule right here, where the outside is this e to the exponent, which when we take the derivative of the outside, we're just keeping e to the exponent, and we keep that inside function of 3x. We just need to be sure to multiply by the derivative of that inside function, which is 3x. So we're going to multiply by 3. And then minus e to the 3x times derivative of x to the 5th, which is 5x to the 4th. All over x to the 5th power to the 2nd power, so you multiply those for x to the 10th. All right, I'm going to see if I can get some common factors out of here. Looks like we can factor out an e to the 3x. We can also factor out an x to the 4th. So I'm going to go e to the 3x, x to the 4th. And then our leftovers, we'll still have an x left over for that first term and a 3. So we'll have a 3x minus, and then that second term, all we'll have left over is the 5. All over x to the 10th. And when we do that, we can cancel out some x values. So if we take out 4 from the numerator, take out 4 from the denominator. And there it is. Oh, that was nice after that last example. 3x minus 5 over x to the 6th power. All right. This one here, doing the derivative, we're going to have chain rule. So we have this inside function of t squared plus 5 up in that exponent, but at the outside of everything, we have e raised to a power. So taking the derivative of the outside function, so derivative of our exponential function, we just keep that base of e and then keep the inside function. And then we're going to multiply by the derivative of that inside function. And actually, I'll write this out as a separate step. So we're taking the derivative of that t squared plus 5. So in the derivative, we have this e to the t squared plus 5, and we're going to multiply with the derivative of t squared plus 5, which is 2t. And that would be done. All right. Find the slope of the tangent line of f of x equals 2 times e to the negative 3x at 0, 2. So notice with this one, we only want the slope of the tangent line. We're not looking for the equation of the tangent line. So really, with our steps for finding the equation of the tangent line, all we need to do is that first step. So we're going to take the derivative. So we have our function, which is 2 times e to the negative 3x. Grabbing the derivative, so we have this 2 multiplying on, so it's going to keep multiplying, and then this derivative of e to the negative 3x, So chain rule, we're going to have e to the negative 3x times the derivative of that negative 3. So our derivative function is a negative 6 e to the negative 3x. And we want to find the derivative at x equals 0. So we're going to find f prime of 0, which will be negative 6 times e to the negative 3 times 0, which is negative 6 times e, and then that exponent is just going to be 0, and anything raised to an exponent of 0 turns into a 1. So we end up with a slope of negative 6 would be our answer. We could go on and find the whole equation of the tangent line by then plugging this in and solving for our y-intercept. So we could go further with this one, but let's go ahead and leave it there. All right, let's take a look at a word problem. So buying organic fruit and vegetables, we have the amount in billions of dollars spent on organic food, and then T is in years after 1995. So we have this exponential function of 2.43 times e to the 0.18t, and we're just using years 0 to 15. So estimate the amount that Americans will spend on organic food in 2009. So with this one, this would be T equals, so we're taking 2009 minus 1995. So we're working with T equals 14. So let's find A of 14 by taking 2.43 e to the power of 0.018 times 14. And we're just going to plug that into a calculator. So 2.43 e to the 0.018 times 0.18. That would have given a very different answer. 0.18 times 14. And we are getting 30.20. And that's in billions of dollars. Estimate the rate at which spending on organic food was growing in 2006. So this is T equals 11 here. And this rate of change at that specific point, that's the whole idea of our derivative. So what we're going to do is find our derivative function and then evaluate it at T equals 11. So we have this constant multiple of 2.43, so that's going to keep hanging out. And then e to the 0.18t, so we're going to keep the e to the 0.18t, but then we need to multiply by that inside function, which is the 0.18. So simplifying this, we're going to have 2.43 times a 0.18. See how messy that is? Not too bad. 0.4374 times e to the 0.18t. And we're going to plug in 11. So 0.4374 e to the 0.18 times 11. And if we just plug that into a calculator, we should get 3.1. Let's go ahead and round this to 2 decimal places. So what does that number mean? So this is a rate of change. And what you can do is think of how A of t, our original function is, let's go input and output. So input is year, output is billions of dollars. So if we think of this as slope, which is exactly what it is, you always take the units of the output over units of the input. So this is dollars per year. So because this is positive, that's where we're seeing that it's growing. So what we can do is say spending on organic food is growing in was, it's the past, was growing in 2006 by $3.17 billion? Yeah, billion dollars per year. So the value we're getting out is a rate, so we want to make sure our units show that. All right, that was a big one, but there were exponential functions, some chain rule practice, as well as a good word problem.